is not only we want to know the time scale, we also want to know the energy, the intensity of the oscillation. Some oscillations are very intense and with very large amplitude. Others may not. So to define the time scale and the amplitude are both important. And ideally, we also want to know the joint, the joint frequency and the density distribution. This usually are not possible. In the past, we are doing, for example, we're doing frequency analysis. The frequency analysis is actually Fourier analysis. We know that some indication of the time scale, and associated with that time scale, with some energy indication, the energy density indication. Yeah. But those energy density indication are actually averaged over the global domain. The frequency is mean, the energy is also mean. But if we want to know the joint density and frequency distribution, that means we want to know the local instantaneous frequency, instantaneous energy. And that will give us the indication of variation and give us a much more detailed, much more clear indication of the variation. So to do the joint energy density distribution, then we have to do AM-FM decomposition. AM means amplitude, FM means frequency. Now, if we can do xt equal to at cosine theta t, at give us the local energy, theta t give us the local frequency or local time scale. So that will be ideal. So this is our goal, is that the question is that for any given data, can we decompose it into components that will have a representation of AM and FM? Yeah. If we can do that, then the Hilbert transformation can offer us meaningful local frequency and local energy for each of the IMFs. For complicated data, there should be more than one frequency, and at any given time, there should be more than one frequency and one energy density. And this is not the case for many of the so-called time frequency analysis. And later we will introduce that method to you. For example, Wigner-Weil. Wigner-Weil has been used by many people and actually by many books. The title is time frequency analysis. Turns out it's to talk about Wigner-Weil. Wigner-Weil does not give you many different frequencies. They offer you one given frequency at given time. Yeah, one given energy density at a given time. But we can imagine that the natural phenomena sometimes is not different from like we go to a concert hall to listen to a symphony. Yeah, the symphony performance, there are all kinds of different instruments. There are drums, there are horns, there are violins, there are all kinds of string instrument, wind instrument, and percussions. So when we listen to the symphony, we feel pleased and we feel we enjoyed it because there are so many different kind of sounds. And if you listen carefully, you actually can tell which instrument is playing and which instrument is playing the theme and which instrument is in response to the theme. Yeah, those are the important elements of the symphony. But if we represent a symphony at each given time one frequency, that means you average over all the instruments to give you just one frequency. That would not be very enjoyable. I don't think so. Yeah. So for complicated data, there should be more than one independent component at each time. That means for a symphony, there are many sounds. Then we have to enjoy the sound. Yeah. The decomposition should be adaptive in order to study the data from non-stationary and nonlinear. And this is very critical, adaptive. Why we have to use adaptive to study the instantaneous, to study the nonlinear and non-stationary processes? If we pick any a priori determined basis, then that base will you have to apply that base to everywhere. And when you apply a given scale to everywhere, you will not be able to study especially the nonlinear phenomenon. Because the nonlinear phenomenon means within one wave, one oscillation, the frequency is changing. And if you define any basis, you may be able to work for certain part, but you will never be able to get actually within one oscillation to separate to define different kind of frequency. So in the past, most of the data analysis or rather data processing method are in the frequency domain. The frequency domain is actually done by Fourier analysis and its generalization, the so-called harmonic analysis. Wavelets fall in that category, the generalized Fourier analysis. So if you do that, then that operation is primarily in the frequency space. And once you get into frequency space, it's very difficult for you to do time domain, to track the change. You may be able to do certain time variation. For example, when you do Fourier, that frequency is global. Of course, you cannot see the change within time. Yeah. But if you do wavelet, you will be able to see some variation with respect to time. But as we will discuss in more detail, even if you use Fourier, even if you use wavelet, the wavelet still will not give you the intra-wave frequency modulation. And also, even wavelet, it's an integral transformation, and it will not give you the intra-wave frequency modulation. It will also suffer the so-called uncertainty principle. You cannot define time arbitrarily precise and also frequency arbitrarily precise at the same time. So, so we have Hilbert transformation. Now, why Hilbert transformation by itself is not enough? Yeah. The Hilbert transformation, it's the original inspiration for me to develop the method. But I find Hilbert, even though mathematician has told us that the Hilbert transformation exists for any function of LP class. That means if you have any function, and if you raise the function to the p power, and if that integral exists, then Hilbert transformation exists. Hilbert transformation exists for all kinds of function, LP class function. But that's not enough. Why it's not enough? Let's look at the primary problem is because you cannot define envelope very well. Let's look at two examples. We'll only take a short time limit. We have sine 1/16, 1/128. Yeah. And the only difference, they are both x1 and x2. They're both sine function. One is with the higher frequency has a small amplitude, and this one is lower frequency with smaller amplitude. Let's look at what Hilbert transformation will give us. The data set 1 is that we have the higher frequency with small amplitude. And this function looks like this. Yeah. The basic large frequency is very clear. But superimposed on that, there are small oscillations. This is a very simple function. only two components, sine A and sine B. Okay. If we take this function and do a Hilbert transformation, what do we get? We get a very nice picture, almost like a flower. Yeah. Yeah. So you can play with this. You can generate all kinds of nice patterns. Yeah. This is one of this very simple pattern, and it goes like this. Yeah. This is the Hilbert transformation of the previous function. Now, if we compute the amplitude of this, here, this horizontal axis is the real part. The vertical axis is the imaginary part. So we have both real and the imaginary part. Then we can compute its amplitude. Right? This amplitude, when you compute the amplitude and plot the amplitude on the data, what do you find? The amplitude look like this. Yeah. Each of these little oscillation is one of these little waves. Yeah. So Hilbert transformation will give you this kind of amplitude. How can you use it? This amplitude, if we use the amplitude as envelope, and this is the envelope, this envelope does not make a whole lot of sense. Yeah. Now, for example, if we identify all the maximums, and then we connect the maximum with the a straight line. So depends upon how you define envelope. The envelope says envelope is a connection of all the maximum. It's this brownish yellow line. And if you say envelope is the definition of Hilbert transformation, it's this line. So this line, the envelope really does not make a whole lot of sense. And this line is almost like original data. Yeah. So this is why, this is one of the reasons we cannot use Hilbert. Given the data, we immediately do Hilbert. It will not give you sine cosine function, even though Hilbert transformation give you the real and the imaginary part. The real imaginary part, the sum of that is actually this. Now, none of the two envelopes seems to make sense. Yeah, the Hilbert transformation amplitude oscillates too much. Yeah, if you connect the maximum, it's almost look at the original data. Yeah. So which one actually is possible? Yeah. It turns out, even though Hilbert transformation exists, this is a very subtle problem. That many times I say that I don't want to use Hilbert transformation when I get the data. I have to decompose it. And this made the mathematician very mad. The mathematician said, Hilbert transformation exists for any function. Why you have to do it? Okay? Why you have to do the decomposition before you use Hilbert transformation? One of the reasons is what I just showed you. Yeah. The Hilbert transformation, if you use that, you will not get a meaningful envelope. And this, again, make the mathematician very mad. Mathematician always ask me, what do you mean by meaningful? Yeah. Meaningful has to be defined. What is meaningful? And I cannot really tell them why I cannot define meaningful. So I think a long time I finally give them one offer. I said, well, if I follow Hilbert transformation, I will not get positive instantaneous frequency. So that's the bottom line that I can offer. So once the mathematician learned that I want a positive frequency, so they went out and proved that what kind of function, what class of function can give you a positive frequency. And there are many, many papers on that subject, all done by mathematicians. Yeah. Because mathematicians think Hilbert transformation is something holy. You cannot ignore it. You have to use it. And if it doesn't, if you say it doesn't work, you have to tell me why it doesn't work. So I told them that I have to have positive frequencies. It's fine. I'll find all the functions that satisfy the condition of Hilbert transformation. I'll also give you a positive frequency. But the positive frequency itself is not enough. Yeah. If the frequency come out to be oscillating and it does not have any physical meaning, I have no use of it. Yeah. And and also, when we get the Hilbert transformation, we want to have the Hilbert transformation give us a very nice amplitude, smooth amplitude curve. That in general, Hilbert transformation will not give me that. We'll get into that. The whole semester we'll talk about those things. So even if you can give me a set of functions, so this set of functions that have positive frequency, my data may not be that set of functions. What I'm going to do with those set of functions? Those set of functions may have all the nice property, but that nice property may not fit my data. So what I want is to find the interpretation of the data. I do not want to find any function satisfy the positive frequency. Yeah. So this is the conflict or the struggle between mathematician and us, the physical scientist or engineer. Okay? So for the envelope, I think at the least is to make the IMF frequency make sense. Yeah. So for example, if we take the previous function and we do the EMD, what we will have is that they actually consist of two components. These two components, each one of this is an IMF. And with IMF, then I can apply Hilbert transformation. And applying Hilbert transformation, I'll get the frequency without any problem. Yeah. And the second component, I also get the frequency. Yeah. And the IMF and the original data, the difference is very small. The difference is extremely small. In other words, the IMF indeed recovered the amplitude. So for each IMF, the envelope will make sense. For complicated data, we have to decompose it before we attempt to make envelope. Don't use Hilbert transformation whenever you see data. You have to decompose it. Yeah. And once we decompose it, we'll be able to do AM/FM. Let's look at the second example. Second example is the low frequency becomes smaller. The low frequency becomes amplitude smaller. That becomes a modulated, that is more like AM, amplitude modulated frequency, amplitude modulated signal. Yeah. This function, if we do Hilbert transformation, what do we have? We have a different pattern. And this pattern, again, is very pretty. One circle in place of another, and in and out, they will repeat the pattern like this. Yeah. And if you compute the amplitude, whatever, the amplitude doesn't change. Why the amplitude doesn't change? In fact, if you have any frequency, any signal with mixed frequency, Hilbert transformation will emphasize the high frequency components. Yeah. So this amplitude doesn't change, even though the pattern changed. But when you add the real and imaginary part, actually you still get back this kind of amplitude. And that amplitude, compare that amplitude with the line connected at the maximum. The line connected at the maximum seems to be a much more meaningful envelope that we're going to have. Yeah. So even with this very well behaved amplitude function, Hilbert transformation still does not serve as a good amplitude, a good envelope. Yeah. one of the reasons is that function has two spectral lines. And then later we'll talk about this because this is so-called Bedrosian theory. Hilbert transformation always zero in the higher frequency based on Bedrosian theory. Yeah. And Hilbert transformation only represented the higher frequency better. For complicated data, there are many, many frequencies. Yeah. Which frequency you actually emphasize, heaven knows. Yeah. We have give you an example of the length of day. You can look at the length of day. The length of day is a jumble of curves that you will never be able to really get any sense, make any sense of it. So here, the empirical envelope seems to make sense. And so that's actually what we use in the empirical decomposition. So mathematically, when we decompose a function, there are many, many different decompositions. Given each function, there are infinite many ways that you can decompose into components. Yeah. If you run out of the pre-existing basis, you can always do the empirical orthogonal decomposition. You can define any function. And after you define that function, you define another function orthogonal to it. And you can keep on doing this. Yeah, use polynomial even. So there are many, many, mathematically, there are infinite many number of ways to decompose the functions. Yeah. Fourier is one of them, wavelet is another. Yeah. So the one that gives us the more physical insight is the one that is most significant. Yeah. What is physical insight? The physical insight is what really guides me into the empirical decomposition. I identify the extrema as significant. If any process is important, this process has to be produce a local extrema. If the process is important, it doesn't even produce a local maximum or local minimum, that means it's mixed with others. It's not significant. So if you can create, if it's important, it has to have a hump or have to have a valley. So the hump and valley are the ones that I zero in. In fact, when we look at the curve, our eyes are actually guided to the maximum, minimum. Yeah. We will never be guided to the zero crossings. Yeah. Because some of the data may not have zero, may not cross zero. So the maximum minimum actually defines the range of the fluctuation. And that's what I zero in. In general, the fewer the number of the component, the better. This is what we call the sparse representation. The sparse representation now is extremely interesting mathematical discipline now. It's developed into mathematical discipline. If you give me data, how can I represent this data with the smallest number of components? The smallest number of components, of course, will also have to be give you some indication or transmit some meaning of the data. The method that we proposed, empirical mode decomposition, so far is the sparest representation that I have ever seen. Yeah. Later we'll prove actually the EMD, the maximum number of components that you ever get out of the data is log 2 base m. M is the total number of the data. And that's log representation, log sparseness. Yeah. If you have order of magnitude of data number, you only increase by log. Once you take log, it's the exponential. So this EMD is very sparse. very sparse representation. Yeah, the adaptive method that we proposed here actually will give you a pretty sparse and very good representation to give you physical meaning. Yeah. So EMD is an adaptive method that can generate infinite many set of IMF components to represent it. Even with EMD, EMD can still generate many components. And those components depends upon how you select your parameter. So EMD does not give you one answer. EMD is a method can generate many. So our job, one of the big job, is to zero in on how to define, how to find the answer that we want, or the near the answer that we want. Yeah. IMF, or the EMD, empirical mode decomposition, is a method, is a general method, a general decomposition method. Yeah. It's not like a Fourier analysis. This is only sine, cosine. It's already defined basis. EMD is the one that generalize the generate the component. In a way, EMD is something like empirical orthogonal function. Empirical orthogonal function is a method that you can generate to the components. And empirical orthogonal function can also generate infinite many. Yeah. Depends on how you manipulate. The most familiar, most popular empirical orthogonal function generate its component through its correlation function matrix. So it depends upon how you define the correlation matrix, how long the data you use to define the core, then you will have different components. So all the method, EMD is a general class of method. It's not a simple method. Now, as at the beginning of the course, we give this as an example, and this is our data, and the EMD. In EMD, we define the maximum. We, as I said, the maximum minimum guide my eye. The maximum minimum give the significance. If the data cannot generate a maximum over here, then this maximum and this minimum define the variation of the processes. Yeah. So I identify all the maximum, I identify all the minimum, and I draw the envelope. And this envelope, once I draw this envelope, then I use the mean as I explained in the introduction. The reason I do that is try to move the wave to the center line. And of course, once it's not enough, we have to do it twice. We have to do it 3 times. We have to do it 4 times. And eventually, you will see that between the first and the second, the second and the third iteration, the difference is smaller and smaller. Some place you can see some difference, like for example like that, and some place you don't see any difference anymore. Yeah. So this is the way that we gradually push the data into a more and more symmetric representation. Yeah. This is the 4th time. So the procedure, as I said, x minus m1 equal to h1. h1, use h1's data, minus m2 equal to h2, and so on until we get hk. Yeah. We call the hk our first component. And the whole procedure is like that. But if we write it out, what happens? The write out is x minus m1 equal to h1. h1 minus m2 equal to h2. So h2, actually, because h1 equal to this, if you take this, plug in h1 using this term, so h2 actually equals to x minus m1 minus m2. So it's x minus m1 plus m2. So the mean m1 and m2 is cumulative. Each time that you push, it will just be added in. And if you keep on doing this, what happens is by the time you get the case time, it becomes x minus m1 plus m2 plus m3 plus m until mn. Yeah. So the component that you get is from the x, you take away all the means. Yeah. This is not surprising. This is fine. But what is surprising is that once you get this H1, and this H1 is, as we define as IMF. IMF, as we define, is that any function has the same number of extrema and zero crossings, and also is symmetric. And this kind of function has good Hilbert transformation. What surprised thing is the next, is that if x minus c1 equal to r1, then we want to find the second component. We have to use r1 minus the second component equal to r2. And we keep on doing this, then we find all the r canceled, and we have x minus cj equals to rn. If we look at the behind this, look in the detail, what happened is this. So x minus c1 equal to r1. So c1 equal to x minus summation mj, right? It's because whatever it's c1, r1 is all the summations. Yeah. So x equal to c1 equals to x minus summation. So this r1 actually equals to the summation. Yeah. Now, once we use r1 as data, we minus another component, we get r2. So the c2 equals to r1 minus r2. r1 is summation r1. r2 now it's the summation of the spline function. So actually c2 equal to mj minus m2j, the second iteration. So from this we can see that all the components that we generate are all spline functions. It's no longer has any, it almost has nothing to do with the data. The only thing that we have relative to the data is actually the spline function. The spline function has any memory, then that's what we got. So all the components other than the first component has no direct connection with the data. And so x equal to summation cj, this is m1, this is c1, this is c2, and this is, and so on. So what you find is that x minus this and plus, so these two cancel. N minus this and plus, they cancel. So all the all the spline function canceled out. So when you add all this, the only term that you get is x. So you get back to the x function. And that is what gives us the nice decomposition. It's always complete. Yeah, we'll come back to that. So because of this, so all IMF components are the sum of spline functions. Yeah, we demonstrate that it's all spline functions. So we select the cubic natural spline to maintain the maximum smoothness. They are so, because it's the components are functions of are actually the summation of the spline function. So there are so many different kinds of spline functions. Why you select this? We select this to maintain smoothness. Later, next class, I will discuss the spline functions. Yeah. So we will discuss the spline function because spline function is so important in our application. Yeah. And once you going through all the perturbation, you get this. You get this. This is R1, the first residual after many iterations, and that is very different from the initial trial. Yeah. If you go through this, that data will actually give you this many components. 1, 2, 3. And 4 has a little bit change. 5, 6, 7. The change is very, very small. Yeah. So in fact, for this data, you get 4 components to get almost everything. And this data has hundreds of points. So this representation is much, much sparser than most of the other representation. For example, if you use Fourier, for this data, you will get 200 components. Yeah, use 400 points. So this representation has the advantage of very sparse representation. Why we want a sparse representation? If you have a very sparse representation, you have only a few components that it can represent the whole thing. Remember, the data is what you got. All the information is in the data. So if you can decompose the data into a fewer components, and each component should have more information in it. If I divide these components into, say, 200 sine cosine, each sine cosine only represents the 1/200th, even though it's not uniformly represented in each component. But each component, the information content is very small. If we can divide this in 4 components, then each of the components give us a lot of information. Yeah, there's a lot of information. For example, we will say that this has a very large oscillation plus medium oscillation, and finally the higher frequency oscillation, and that's it. Yeah. So with this decomposition, then we can define the frequency very well. This frequency is not through integral transformation. This frequency actually is through differentiation. Time derivative of the phase gives us frequency. It's like the velocity is defined as differentiation of position. Yeah. Frequency has many different definitions. And later, when we talk about instantaneous frequency, later we will come back to visit it. But here I will give you certain definition. Say, for example, frequency can be defined by Fourier analysis. The Fourier analysis is that the frequency is the Fourier transformation, and then that omega is my frequency content. So they got many, many different frequencies, but all the frequencies are constant throughout the time domain. Then we have wavelet. Wavelet, even though people will not talk about wavelet in terms of frequency, they talk about wavelet of color, of scale, of whatever. All of that can be converted back to frequency. It has to be, yeah. Because it's the dilation and translation. The dilation is the time scale. Translation is the position. So that the dilation scale is a time scale, and inverse of that time scale is actually frequency. So I always plot wavelet in terms of frequency. Yeah, I do not follow their argument of dilation scale, whatever. It's the same thing. Yeah. Then Wigner-Weil analysis. These 4 are very well established harmonic analysis. It's all based on generalized Fourier transformation. Once you get into the dynamic system, however, you get something different. This is that if you have a dynamic system, if you can define Hamiltonian of the dynamics, okay, then you can compute the action. The action is the integral of generalized momentum and the generalized position. Yeah. So you integrate that you get action. But because of this action, definition of action is integral. So it's an average value. It's not the instantaneous value. Then, if you operate using this as an independent variable and take a differentiation of Hamiltonian with respect to action, you get a frequency. This frequency is the frequency that is given by the dynamic system. Yeah. And that frequency seems to be instantaneous, but it's not, because the variable is not instantaneous. Variable is already integrated. Yeah. Then later we'll have Tigger energy operator. We can have a generalized zero crossing, and of course we can have HHT, that including Hilbert and the quadrature. Yeah. And eventually we will all get into discuss. This whole class will get into discussion mostly of this, sometimes of this. And for comparison, we will talk about the Tigger. The effect of shifting, as I explained up until now, there are two, serves two purposes. The first one is to eliminate the riding waves. We cannot allow a wave right on top of another wave. If a wave right on another top of the wave, that means between zero crossing you have two extrema. Two extrema means that you have a maximum, a minimum, maximum, minimum, and a zero crossing. We cannot accept that. Why? Because if you have that, then in the Hilbert transformation or any other method, you will find that the real part will increase and decrease and increase. So in the phase domain, you will have a double valued function. And that double value function will definitely give you negative frequency. Yeah. So because you have to come down and up and up, down. The imaginary part may not be, because the real part has double value locally. It's not going to be monotonic. Then the second effect is to make the envelope symmetric. We do need the envelope to be symmetric, otherwise we'll have eccentric circle. The Hilbert transformation will not be a circle near zero, but offset. Once that offset, we again will get very funny frequency values. This frequency, the phase function is defined by real versus by the imaginary versus real arctangent of this function. So time derivative of this function, time derivative of this theta function actually can be written out to be like that. And this, if you expand it out, it can be written like this, and if we factor this amplitude out. And what this indicates is that if you have dy dt or dx dt or either imaginary or the real part, the derivative is zero, has absolutely no problem, because that's well behaved. If dy dt equal to zero, it's fine. Dx dt is zero, it's fine. Yeah. What is not fine is when amplitude equal to zero. If the amplitude equals zero, you have a singular. Amplitude cannot be zero in this in this expansion, in Hilbert expansion, or in any expansion. When will amplitude be zero? Amplitude will be zero is when you have overmodulation. Overmodulation is that if you have x sine x plus sine y, yeah. If the x and y are almost of the same amplitude, then it will modulate and become zero and then modulate again. So the envelope is positive, it will go through zero, becomes negative, and then goes through positive. So envelope equals zero imply envelope will change sign. Yeah. The envelope change sign cannot be tolerated here because it will give us a singularity. Yeah. Now, in our expansion, the envelope will never change sign, yeah, because we always define as a positive, yeah. So that we have to be very, very careful. That is, so when amplitude becomes A becomes 0, then we may have singularity. Now, amplitude can actually get pretty close to 0. And any time amplitude gets close to 0, we may experience a very large frequency. And that frequency sometimes is not really reliable. So when amplitude is small, this frequency tends to fluctuate very, very large. And we'll see that later. Now, the maximum number in this is a precaution because at the beginning, when we develop this method, we don't know whether it will converge or not. Whether you can iterate it a finite number of times, you can exhaust it all. It's not certain. We're not sure. So at the beginning, sometimes we find a different kind of spline. Okay, it actually does not converge. The computer will sit there and keep on doing it, and we don't know when it will stop. By the time we run many times, and then we finally stop, and then we get the answer doesn't make sense. So to save time, we have instituted a number n. This number n is the maximum number of iterations that we can tolerate. Yeah, and as a result, that got left in the operation. Yeah, it's not important anymore. But but we we have keep that as a as something, especially in the initial software. The present software does not have that. The present software, the initial software, the stop criteria is slightly different. Yeah, the stop criteria, I have presented mostly this stop criteria just to make the mathematician happy. I seldom use it. At the beginning, I did use it, but later I found it's very cumbersome. It's very slow. I have to check this every time. It's very slow. When mathematicians see this, they are very happy. They say, "Oh, okay, this is a Cauchy criteria." They say it's fine. Yeah. The meaning is very clear. That I do not want. I will stop it when I have the difference between the two components become small. Then I don't care. Yeah, that's my meaning. But the mathematician wants to write out in this form. Says, okay, hk minus 1 match hk becomes small. This criteria translated in different form is if the mean is small, then pre-assign the number. So the maximum minimum average is small. That means the variation is small. And it's very similar to this. The French people, Patrick Flandrin, if he used his software, he used this criteria. So if the mean is smaller than a pre-assigned value, that means the envelope, maximum envelope, minimum envelope, I squeeze until the envelope becomes a straight line. But it will never become a straight line. Fine. That if I, the pre-assigned number is I take 0.01 of the maximum amplitude. It's less than that, I stop. That's this criteria. I have used this criteria very often, and the reason I use that criteria is that at the beginning of the development, I'm very careful about whether the function is or is not IMF, intrinsic mode function. To be intrinsic mode function, of course you can see the mean has to be 0 and all that, but those are computationally extensive. So the least extensive computation is to count how many extrema you have and how many zero crossing you have. If they agree, then I think it's okay. So at the beginning, to develop the operation, I define a S number. The S number is that if I I did this shifting once, and I will count maximum and count minimum. Count the zero crossing. The extrema number and the zero crossing, if they agree, I will do it another time. I say, maybe I'm lucky, I'll do it another time. If the second time, they also agree. Not only they agree, the number has to check. For example, the first time I've counted 100 extrema. The second time I also counted 100 extrema. So this means S number equal to 2. So I can set as well, I need X number equal to 3. Then we'll do another time. Another time, another extrema come up. So instead of 100, become 101. So then I reset the S number. So this is the first time equal to 101. I do another time and another time. So it's 3 times, it's all agreed, then I stop. So using this method, I have written a paper to check the whole operation to see whether if I set S equal to 2, S equal to 3, S equal to 20, 20 consecutive times, I have to have the same number of extrema and same number of zero crossing. If that satisfies, I stop. So apparently, you can set this number to be any number to any value. So I have checked for many, many different values. Later we'll get into that. Okay, and I find that indeed there is a range of optimum. You should not select this as very, very large, and you shouldn't select it as very small. In other words, if the first time you get S equal to, say, extrema equal to zero crossing, stop, and that's very risky. So I have been using this consistently until very recently. Very recently, Dr. Wu come up with the ensemble EMD. And in that, Dr. Wu has been consistently pushed for this criteria. And this criteria happens to be the criteria used in the software that's posted on our website. This criteria means that I don't care whether the result is IMF or not IMF. I will do 10 iterations. After 10 iterations, I stop. You know what? The mathematician likes that. The mathematicians always keep counting. It's too complicated. And the counting is every time is different. If you tell me just do 10 times, it's fine. We'll do 10 times. Or you can say do 20 times. But 10 times and 20 times, they're all fine. We will later discuss why this is fine. Okay. And in fact, the more time you do the iteration, the amplitude will become more uniform. Because each time it will squash it a little bit, because that's zero. That means it will never be zero. So each time you have to push it, it becomes a little bit uniform, a little bit uniform. If you take the fixed iteration, if you say that I'll do it 1,000,000 times, you know what will happen? Every component come out to be the amplitude, to be the constant. So we have a conjecture. That is, if you do it infinite many times, and nobody can do infinite many times. Okay, we did it. I did it. Tried 1,000,000 times. It will come out to be ridiculous. Okay, so if you do it enough times, what will happen is that each component almost becomes a sine function. But it's not an exact sine function because the frequency cannot be exact. The size, all uniform. The frequency still have a little bit. So if you do it enough times, it will reach almost sine function. That is, the amplitude is no longer variable. The frequency is still variable. It becomes FM. And at that time, however, it's no longer for finite data, it's no longer orthogonal to each other. Yeah, and all kinds of problem appears. We will talk about that. So right now, sometimes I still use this, and most of the time I'm using this. So the software posted on the web, it's this. The software that I use, in addition to this, I also have that criteria. Yeah. But this software, I cannot post it on the web because that's NASA software. NASA has patent on this whole operation. So if I post that on the web, then NASA can sue me for breach of their patent protection. So, so we post this data. This approach, it's not patented by NASA, so we can use it. Yeah. Another thing is curvature. When we look at the data, we look at identify maximum minimum. But many times, the data maximum minimum, of course, define the function. But this also defines time scale. The inflection point also defines. See, when we look at this, we say, okay, this is time scale, this is time scale, this is time scale. How about this? Here is also time scale. Here is also time scale. So there are many, many different ways to define time scale. So why should I only use extrema? So if you start to consider others, so what we define, so we define x prime equal to 0. That's extrema. Take a derivative equal to 0, we identify those points. We'll connect those points, okay? But how about x double prime equal to 0? If you say x double prime, how about x triple prime? Yeah, we can keep on doing that without n. In fact, the x function, if we use Taylor series expansion, it equals to, if we take all the derivatives, we can define the function perfect. Yeah, Taylor series, it's always, within that neighborhood, it's always converge. Yeah. So if you have all kinds of derivatives, then it will converge. But you think that this is great. You think that, fine, if I know the local property of the function, I know the whole function, right? Because if I know all the derivatives, then I will be able to define the function. But it's not that free. The reason is that xa defined by 1 point, a. When I have x prime, you cannot define prime with 1 point. You have to have 2 points to take a derivative. Two points difference, dx, dt. Dx means you at least has 2 points to get the dx. 1 point cannot compute the dx. Right? So by the time you get here, this is 1 point. Here you get actually 2 points. How about this? Second derivative. Second derivative is the variation of derivative. So you have to have a derivative at 2 different points. That means at least you have to have 3 points. Yeah, and so on and so forth. By the time you have n derivative, that means you have to have n points. You have n points, then you can represent the n points function. That's fine. So Taylor series expansion does not give you anything free. If you want to know the function for n point, you have to provide n points. Its only difference is that instead of writing the function, it writes the function in terms of derivative. Yeah. So because the derivatives are so important, it actually can be written into Taylor series. Where should we stop? Should we stop at this, or stop at this, or stop at this point? So I decide to stop. I will not go beyond curvature. Yeah. Curvature, we can still see. we can still see a hump, a inflection point that's visible. Then we can still see it. And also, my background is mechanics. Study the force, balance of the force. And in mechanics, with all the shortcomings of Newtonian mechanics, we still use it. Okay. In Newtonian mechanics, however, if x is position, then the first derivative is velocity, the second derivative is acceleration. Beyond acceleration, there's no physical meaning. At least Newton says, well, it's not important anymore. Okay. Second derivative is all we need. Okay. So based on that, I stop. There's absolutely no other justifications. If you want to go higher, do it yourself. But be prepared for the consequences. Yeah. Even curvature, it's kind of hard to defend a lot of time. If we decide to do curvature, we have to be careful of what we ask for. Yeah. Many functions, actually, when you apply to, later when we talk about Duffing wave. Duffing wave is you know, when at the beginning we say that the pendulum keeps changing length, that's a Duffing wave. If you use Duffing wave, the Duffing wave component becomes two components. Yeah. Originally very nice explanation says frequency is changing, modulating, and all that. Then it becomes two frequency. How you explain this two frequency? Yeah. That's hard. So we do have this, but I use it only sparsely and only in extreme case I use it. What it's used for? It's very useful for the first few components. If the data is extremely noisy, yeah, I want to get rid of the noise. Then you take a derivative and get the data even more noisy. Then you throw away the higher components and reconstitute the data. The data becomes much smoother. I use that as a local filter to make the data smoother. Other than that, I do not use it very often. Now, having said this, having said that extol the virtue of EMD, does EMD have a problem? Of course. Here is one problem. That is mode mixing. Sometimes you have data, the data scale becomes mixed. For example, I have data like this. This is a sine wave. At the beginning, I talk about, say, non-stationary, non-linear, right? This is non-stationary. I have this higher frequency someplace, and not at the other places. Yeah, intermittency. Intermittency problem is very common. Yeah, it appears everywhere, especially in, for example, in fluid mechanics when turbulence first starts. Turbulence is not consistent, not all the time. Turbulence occur occasionally and then disappear, occasionally and then appear and disappear every now and then. If you ride the airplane, you'll find that every now and then the pilots turn on the lights. There's a tighten your seatbelt because the clear air turbulence. Clear air turbulence does not exist everywhere. It's only someplace. And if you do not care, be careful, then you may hurt yourself riding through this intermittency. That's this. Yeah. Now, I have said that this method will work for intermittent, for all kinds of data. If we have data like this, what happens? We can still do the decomposition. The decomposition is the following. The decomposition will immediately get the higher frequency components out without any problem. But when you take the higher component out to be the first component, the place that has no higher component, the envelope will go through all the maximum through here. So this component get emitted, the large component get immediately get extracted out. So the first component then has, the first component look like this. And this component, the first component here has a small scale as well as large scale. And this scale mix together. And that is not physical. The reason it's not physical is that we know in the mechanical system, each process will generate a specific scale. The process that generates the tiny scale cannot be the same process that generates the large scale. Okay, so if you ignore that, you just keep on doing this, then what will happen is that you get the first component, you get the second component, you get the third component, and so on. But actually, the real problem is like this. You have a small wave at a certain spot, and you have a continuous large wave. If we can decompose the data in the it depends upon how to say it. In this panel, it's great. But in this panel, it looks fragmented. You cannot see the physical phenomenon very clear. Yeah. At the beginning, I noticed this. I know this will exist. I said, there's no problem. But if I project this into time frequency domain, then the time frequency domain, then the higher frequency and lower frequency will fall into its proper place. Yeah. I thought that will happen. Indeed, it happened. What happened is this. So we decompose, we have two different kinds of decomposition. If we constitute this into the Hilbert spectrum, we get the two answers. The left one, with the mixture, we have the higher frequency very clear. We have the lower frequency somewhat clear. And we have it. But compared to this, we have high frequency very clear. We have low frequency extremely clear. These two are very different. And if we look at the details even tells even more. That is, this is the higher frequency component, this lower frequency component is pretty continuous with some little breakage. But this get wild. Yeah, it's generally in that area, but it does not convey very clear signature. It looks as if it has many, many different waves, just like this shows. Just like this shows, there's many, many different waves over here. Yeah. So this is a problem, and if we can consistently get this kind of answer, that's much better. And if we do marginal spectrums, what do we find is this. The top one, the blue one, is the Fourier analysis. The Fourier analysis gives us a higher frequency, components in higher frequency components here, higher frequency, and low frequency components is much more energy in low frequency components. So Fourier gives us this signal has two components. But these two components, however, if you use Fourier, you try to reconstitute the signal, you will think that we have consistent high frequency and a consistent low frequency. The intermittency, the property of intermittency disappears in the Fourier representation. Now, in the marginal spectrum, of course, the time elements is not there. But if we look at this without intermittency or the straightforward decomposition, we will have the lower frequency so smeared over a very large range. Yeah, but this one is much better. This one has a much deeper, much higher dynamic range than Fourier. Fourier has about 1 decade. This has about 5 decades. Yeah. So how did I get this? How did I get this answer? I get this answer by the so-called intermittency method. The intermittency method right now has not been used very often, but I think it's still useful. That's why I introduced this to you. Right now, we have a better way. We will do ensemble. Ensemble would did away with many of the problems here, but ensemble also generate another set of problems. So therefore, I think the intermittency is still useful. What's the intermittency? Intermittency is that when I decompose, I say that I will use 100 times, and I use 10 consecutive counting, and first time I set a parameter A. A means that any wave shorter than 8 points, I will ignore. I will totally ignore it. I'll only look for the wave for shorter wavelength. Yeah. So by setting this, the first components I got, are the shorter waves. The wavelength is shorter than this. To do this, I have to know how long the wave is. Yeah. So this may not be an easy task. For this particular problem, it's very easy because I can identify the short wave. For a continuous random signal, sometimes it's not possible. Okay. So this is the so-called intermittency method, and I've been using it for a while, and actually it works for many areas. It's much better. Later we'll discuss that. So if you use the intermittency method in this particular example, we actually get a much better low frequency definition. And as far as high frequency definition, it's hard to say which one is better. So we'll look at the low frequency, the Fourier analysis, and the one that with intermittency almost provide the same answer. The difference is over here. This, when you plot in log scale, it's very obvious. When you plot in linear scale, it doesn't seem to be significant. Yeah. But in log scale, you can see that low frequency is this versus that. It's very different. Yeah. In linear scale, it does not. And the one that is really bad is the one that is EMD without any straightforward EMD. So straightforward EMD, you have to be careful. If there are severe mode mixing, it may not give you good answers. But when we look at a higher frequency, the higher frequency, it's obvious. Even though in log scale, the higher frequency, Fourier seems to be very coherent. But higher frequency, look at it. Both intermittency and without intermittency, higher frequency has a very narrow spectrum, even though this has some noise, sidebands. But if we look at this, in this linear scale, what you see is that the higher frequency definition with intermittency, without intermittency, are all better than Fourier. Why this is all better than Fourier? Because Fourier is a frequency from beginning to end. It cannot stop. So to simulate, certain wave appears now, but late appears here and there, not everywhere. It will have to have many, many waves of many, many different frequencies to cancel out the place that without wave. So instead of the true wave here, true wave frequency here, you have to have this, you have that, you have this, you have that, you have symmetric sidebands just to cancel out the part that without wave, the part that's quiescent, it's quiet zone. So that is why the Fourier analysis will not give you good answer if the signal is not stationary. Yeah, if the signal is consistently certain way, Fourier is fine. If the signal is not consistent, intermittence, it happened here, not happened in another place, the Fourier will end up with all kinds of sidebands. And these sidebands has absolutely no physical meaning. But mathematically, without that, you will never recreate the phenomena that you observe. Yeah, that is one of the strong reasons that I propose this different view of data. Yeah. So for high frequency, we can be very sure that this is the frequency. Yeah. And this frequency appears only in certain spot. That appears only at this location. So with this, then we can get this answer clearly. And this intermittency, we have to be careful to record what we use. Why we have to record what we use? Because IMF generates infinitely many different components. Yeah. So we have to record that we use total number of spline, total number of iteration, what the stoppage criteria is, what are the criteria we use, what kind of rejection criteria we use. Yeah. So mathematically, the mathematician has a certain set of requirements for bases. IMF is generated base, and this base, the requirement is complete convergence, complete orthogonal uniqueness. Those are what the mathematician want the base to satisfy. So convergence, we don't have any proof. State in the mathematician's language is that for given epsilon, there exists a large n. Okay, such that at the nth envelope mean Mn is less than epsilon everywhere. This is a convergence. Can I prove that? No. Can anybody prove it? No. No one can prove it right now. And I made this statement to the mathematicians, so prove this. Nobody wants to prove it. Nobody can prove it. The reason is that the iteration, the spline, is still somewhat vague in mathematical terms. They can define spline, but they cannot define the property of spline so precise as to get into the mathematical proof. So to give an arbitrary number epsilon, there always exists a large finite n such that the nth mean satisfy this. Yeah. This convergence is not proved. But what we did is that given another problem is that given a large n, then there always given epsilon, there always exists a large n, so that this number will eventually become small. Even that they cannot prove. Yeah. So you cannot prove that. So for given epsilon, there exists n, such that the difference between nth and n-1 trial is less than epsilon everywhere. Even this they cannot prove. So I posed this to the mathematician. I said, all right, I know I cannot prove it, but I can apply this method to any problem. This always works. But always work is empirical. Okay? It's not analytical. Analytical, you have to say that if you give me this function, it always work. I cannot prove that. Yeah. So I propose this to mathematical community. Yeah. So another problem is we always have finite number. empirically I can say log 2 to the n. I've never go beyond that because it's static. Yeah. But strictly mathematical proof, I don't have. So I went to Princeton University, looked for the math professor, and asked the math professor to help me. And they joined together with me. We wrote a proposal. We said, we're going to do all this, but I don't think we can do it. Yeah. But research is that you have a good intention, you may not get the answer. Yeah. This will be a long process. Yeah. Another thing is that for given m of the total number of data points, log 2 to the m has not been proved. It's observed. It's an empirical fact. Yeah. Now, so the converging condition, it's not known. But I do know one thing, that I use upper and lower envelope. It works all the time. Somebody at the beginning, I also tried. I said, well, I have to draw upper and lower envelope, and that is too time consuming. What if I have a maximum minimum, I determine the midpoint of maximum minimum. And then I can draw one spline curve to go through the mean point. And that should be easier. And it turns out that approach does not converge. I know that for fact. Yeah. And I can almost prove that it's not converging. So convergence problem now stands in this state. Completeness is trivial. Completeness is all, I can prove that. Completeness means if I write x equal to c plus rn, I use the rn as another term. Yeah. This always represents the whole data. Why? You have already known it. Because each of this is a summation of spline. And the spline all cancel out. So finally I get back to my original data. So there's no problem. If I add all this together, I get my original data. There's no magic at all. This is algebraic. So completeness is proved. Orthogonal. Orthogonal means that the inner product of two components is always 0. Yeah. Now, Fourier component is orthogonal. Orthogonality usually is demanded for linear functions. Nonlinear decomposition doesn't work. So Fourier is linear, it works. But in our decomposition, even it's linear, even it's nonlinear, it still almost works. And another thing is orthogonal. In Fourier case, is for infinite long data. Finite data is not orthogonal. You take 2 sine, cosine. If you only take, say, 3 waves, you try, they are not orthogonal. But if you have the sine, cosine, it becomes infinite, it's orthogonal. So it depends upon the length of the data, it depends upon the basis. Now, in our case, why we demand orthogonal, even though we are nonlinear decomposition? We demand orthogonality is because we do not want the cross term to get into the energy. Yeah. If the cross term get into the energy, then that may create a problem. You think, well, that's perhaps not important. If you alloy it, sometimes you get negative number for energy because the cross term may overpower the data. So we have to insist that this term to be 0. And even though I have never demanded this term to be 0, but it's always 0. Why? Because the decomposition actually is a Reynolds type decomposition. What is Reynolds type decomposition? Reynolds, Osborne Reynolds, is a great physicist. He is the one that start the study of turbulence. Yeah. What he did was to let the flow through a pipe to observe the flow when the flow becomes unsteady and becomes turbulent and mixing. If you have a pipe, you let the water flow. When the velocity is low, the flow is very uniform. When the velocity is higher, then the flow becomes oscillating. And when you have extremely high, then it becomes turbulent. Yeah. So he studied the stability, that when the flow becomes unstable. And as a result, he defined what we still call the Reynolds number, but it's the velocity times length over the viscosity. The more viscous, the more stationary, stable. Like water, it can flow and it becomes unstable. But if you use oil, it becomes more stable. And if you use honey, it becomes even more stable because it's very sticky. Yeah, it will never really becomes unstable. Using that, Professor Ronald Smith at Yale University think that everything's flow, everything's fluid, everything flows, yeah, and including rocks, yeah. We know glass definitely flows, yeah. Glass, if you take a old glass panel, if you go to Corning Museum, you find that old glass panels stand there for a long time. Actually measure the top thickness and the bottom thickness, they are different because it flow coming down. So the bottom glass actually becomes thicker. Yeah. Rocks flow too, and they use actually, they call the geological fluid mechanics. Yeah. Define the viscosity to be huge. Yeah. It takes millions of years for the rock to flow in the bed. Yeah. You go to the field, you will see the rock layer sometimes fold, and they define that as a flow. So Reynolds, Osborn Reynolds, using velocity, decompose velocity into velocity mean plus a perturbation. Mean and perturbation products are always zero, by definition, because this is a constant, this is fluctuating. Fluctuating, multiply the constant, take a mean, is always zero. Yeah. So Osborn Reynolds decomposition is always orthogonal, the mean and the fluctuation. In a way, EMD is taking the fluctuation from the mean, taking fluctuation from the mean. The only difference is the Reynolds define mean as overall mean. We define mean as local mean. Yeah, our mean does not have a global significance. We only have local significance. Yeah. So orthogonality is checked by this definition or this definition. This is two components. This is all the components combined. Yeah. So I always check components. For example, this data, when we decompose in this form, the orthogonality check, this is the overall, this is the pairwise. They're all very orthogonal. Yeah. I cannot prove it exact orthogonal because this is Reynolds decomposition. Yeah. Uniqueness. This is a big problem. If you keep the parameters fixed, it's unique. If you change parameter, it's not unique. That's why I insist on recording what parameter you use. So if you use the same parameter, you tell other people, I use this and that, then other people should reproduce your answer. And that is also one of the reasons why mathematicians like the fixed iteration. So if we define EMD as fixed iteration of 10 times, if you use 11 times, that's your problem, that's not my problem. So if everybody uses 10 times, everybody get the same answer. And mathematicians like that very much. Yeah. And in that sense, it's unique. The uniqueness is to the point of the parameters you use. Yeah. So, so uniqueness with respect to the parameter used. The present shifting is based on the cubic spline. If you use different spline, you'll get a different answer. Yeah. So EMD, as we define now, is with the set of parameter and set of spline. However, if I use 10 and I use 11, I create a dramatically different result. That's no good. So there is uniqueness, there's also stability. The answer should be stable. I use 11, I use 12, I use 20, I use 5. The answer is almost the same. Yeah. And that gives us some stability of the method. If the method is not stable, it's not useful. Yeah. So I think the time is up. We'll stop here. Some tricks in the sifting is not necessary. What I did here is that I add a little bit noise that actually help the decomposition. That was ad hoc. I just add a little bit noise and I get a better answer. Later, when I have an ensemble, that's more systematic. Okay, so we will maybe touch upon that later, but it's not important once we have ensemble EMD. So, are there any questions from Tokyo? Any questions?
No.
No questions. Well, thank you very much.
No question. Thank you.
Thank you. Bye bye. Okay, we can turn on. Bye bye. Okay, now we can turn. Now we can talk about real business. You have any questions? 有没有问题？没有问题啊，没有问题我们就下课。OK, class is dismissed.